we've seen that when we have a function y that's written in terms of x, we can differentiate that y term to get dy by dx. This means we differentiate the y equation with respect to the letter x, with respect to x. We can then take that equation and differentiate it again, and when we do that, we get d squared y by dx squared. This is called the second differential, or the second derivative. So let's have a look just at how we do that with an example here. So y is equal to 4x cubed minus 3x squared minus 2x plus 7. The first thing is when we differentiate y, we get dy by dx. So 4x cubed differentiates to give 12x squared, minus 3x squared minus 6x minus 2, and the 7 differentiates to give 0. So we've differentiated once to get dy by dx. Now if we take this term now, it's all written in terms of x, so we can differentiate this again with respect to x. So when we do that, we get d squared y, or sometimes d2y, by dx squared. And we just use the same rules. So multiply through by the power and reduce the power by 1. So 12x squared differentiates to give 24x. Minus 6x differentiates to give minus 6. And negative 2 differentiates to give nothing. So d squared y by dx squared is 24x minus 6. Now we will use that now to help us find what are called stationary points. And stationary points are just points that on a curve where the gradient goes from either positive to negative or vice versa. And one we call a maximum turning point is where just the gradient is going positive, and then after the point it becomes negative. Or a minimum turning point is one where the gradient is negative and then turns to become positive. So here we have a positive gradient, and then out of the turning a stationary point we have a negative one. Negative gradient becomes positive. Now, to do that, to go from positive to negative or negative to positive, you have to go through 0. And so I know that whenever I have a stationary point or a turning point, I know the gradient must equal 0 at that point. dy by dx equals 0. And so that's what we're saying here. But whenever we find a stationary point, dy by dx will always equal 0. When we have a quadratic graph is either a happy face or a sad face. And so when we have a quadratic graph, we will have one stationary point. However, when we have a cubic graph, often we'll get one where we have one maximum and one minimum turning point, one sad face and one happy face. And we need to be able to distinguish between them. So to find a stationary point, we always start by putting dy by dx equals 0 and solving. To find out which type of stationary point it is it a happy face or a sad face? Then we check the second differential. And if that second differential is less than 0, if it's negative, then that implies that, the way I remember it, it's an unhappy face. If you're negative, you're unhappy. And so that's actually a maximum stationary point or a maximum turning point. However, if you find that your d squared y by dx squared is greater than 0, it's positive. Well, if you're positive, it implies you're happy. And so if you draw a happy face, you can see that that's a minimum stationary point. So we're going to use these properties in the next couple of questions just to find and determine what type of stationary turning points we have. So here we go. Y equals 3 minus 4x plus x squared. Find the turning point or the stationary point and state its nature. So the first thing we want to do is find dy by dx. And when we do that, we're going to get 2x minus 4. I always like to write this then at stationary points. Whenever we want to find a turning point or a stationary point, dy by dx equals 0. So write that down. And then let's put our dy by dx equal to 0. So 2x is 4 and x is equal to 2. Now we're asked to find the turning point. We found the x coordinate. Let's find the y coordinate that goes with it. Well, y is equal to 3 minus 4 times 2, so minus 8, and plus 2 squared plus 4. So y equals -1. And so the turning point, the stationary point we have, is at the point 2 minus 1. But we're also asked to state its nature. Now, I know that this is a positive quadratic. It's going to be a happy face, but I need to prove it. And the way we prove it is by looking at the second differential, d squared y by dx squared. And we're going to take dy by dx, and we're going to differentiate this. And when I differentiate 2x minus 4, I just get 2. Now, 2 is a positive number, and so for me that implies a happy face. That's a minimum stationary point. So just to finish this off then, we have a minimum turning point or minimum stationary point at 2 minus 1. In this question, we have a cubic curve to find the turning points and state their nature. And first of all, notice it says state their nature, find the turning points. We're looking for more than one. But I also happen to note that the shape of a cubic often looks like that for a positive cubic. So I reckon that the first turning point is going to be a maximum and the second one's going to be a minimum. But it's not good enough for me to know that. I need to prove it as well. So let's see how we do that. First of all, if y equals x cubed minus 6x squared plus 9x plus 3, well, first I want to find dy by dx. So that's 3x squared minus 12x plus 9. And I know if I want to find the stationary points, the turning points, at stationary points, the gradient, or dy by dx, is always equal to 0. So let's do that. Let's put our gradient equal to 0. I can see that all of these numbers are divisible by 3, so 0 is equal to x squared minus 4x plus 3. And that will factorise. Two numbers that multiply to give 3 and add to give 4 are minus 1 and minus 3. And so my two solutions for this are x equals 1 and x equals 3. Again, let's find the y coordinates that go with that. Well, if x is 1, y is equal to x cubed, so 1 minus 6x squared, so minus 6 plus 9x plus 9 plus 3, so 13 take away 6, so y equals 7. So that's the point 1, 7. Wee bit more work when x is 3, y equals 3 cubed, so it's 27. Minus 6 times 3 squared, well that's 6 times 9, so that's minus 54. Plus 9 times 3, so plus 27, plus 3. So in that case, y equals 3. So we've got the point x is 3, y is 3, the point 3, 3. Now those are our stationary points, and I can see 1, 7 is above 3, 3, so it makes sense that the left-hand one's going to be a maximum and the right-hand one's going to be a minimum. But again, I need to prove it, and the way I prove it is by looking at the second differential, d squared y by dx squared. So we're going to take our dy by dx and we're going to differentiate this. So 3x squared differentiates to give 6x, minus 12x to minus 12, and 9 differentiates to give 0. So what about our two stationary points? Well, the first stationary point, I know x is 1. Well, what's our second differential? d squared y by dx squared. Well, 6 ones are 6, minus 12 is minus 6. That's a negative value, which implies an unhappy face, and that's a maximum. How about the other stationary point? Well, if x is 3, that's our other stationary point, d squared y by dx squared is, remember to put it into our d squared y by dx squared. So 6x, 6 times 3 is 18, minus 12, which is 6. And 6 is a positive value, so that implies to me a happy face or a minimum stationary point. So then let's just finish it off. We have a maximum stationary point at 1, 7, and we have a minimum stationary point at 3, 3. I guess theoretically, this is not the maximum value of this curve, so you might see it called some places a local maximum, because if you look at this curve, look, it's the maximum part of this curve, but these values here are all above it, they're greater than it, so it's not the maximum value of the whole curve. So sometimes we call it a local maximum, and likewise we would often call this a local minimum, because it's the lowest part, or the smallest part of this curve, part of the curve. But look, these values of x here, or values of y here, sorry, would be less. So it's not the minimum value of the whole curve. So sometimes you'll see these called local maximums and local minimums. But generally, we just refer to them as maximum stationary points and minimum stationary points.